Hello, my name is Nick, and today I want to teach you about some quicker combinatorials. Though this video will provide some insight behind combinatorial functions and strategies for using them, the goal of this video is not necessarily about intuiting combinatorics. Rather, the goal of this video is to become faster with combinatorics. Today you will learn more efficient methods of calculating, strategizing, and using properties of combinatorial functions. Combinatorial functions are functions that have to do with counting. For our purposes, you can break them up into three camps: factorials, permutations, and combinations. Let's start with factorials. A factorial counts the number of unique orderings of n unique objects. It is the strictest of the combinatorial functions in terms of what it counts as the same thing, and it often produces the largest values of the three. For the quickest route, take n and multiply all the values down to 1. Here's an example. Next up are permutations. A permutation counts the number of unique orderings of k length made from n unique objects. It's slightly looser in terms of what it counts, so it produces slightly smaller values than factorials. For the quickest way to calculate, take the first k values of n factorial. Notice how as k changes, we simply select a different portion of our factorial. Last up are combinations. A combination counts the number of unique groups of k length made from n unique objects. It is the loosest of the three combinatorial functions in terms of what it counts as the same thing, and often produces the smallest values. The quickest route is to just take the first few digits of the factorial function and divide it by the last few. I like to imagine two lines under our factorial function, which help us select which values to include in the combination. Hopefully by now, you're getting a better sense of how to quickly translate between these different functions. For quicker strategizing, just remember the acronym FACT. F stands for factorials. They're everywhere, so if you're in a tough counting problem, one is bound to show up. A is another perspective. Just keep switching perspectives until you find one that actually works for you. C is cut down. If a problem is daunting, simplify at all costs first. And lastly, take order. If in doubt, use that common motto of permutations are when order matters. These four facts are the key to your success. Here are some common problem setups for permutations and combinations. Counting stacks of cards from bottom to top is a permutation problem, while hands of poker is a combination problem. Unique strings or license plate numbers versus groups of letters is also a big one. You can have ordered pickings of people or unordered groups of people. And lastly, counting ice cream cones with multiple scoops is different from counting bowls of ice cream. To quickly remember combination properties, you can draw out Pascal's triangle. To draw Pascal's triangle, first start with two rows of ones. To build the next row, take each adjacent pair of numbers and put their sum directly below and between them. You can continue this process to keep building further rows. The first property of this triangle that you might notice is that every entry is actually a combination. In fact, it is every combination. Any n choose 0 is 1, and any n choose n is also evidently 1. Our triangle is symmetric. This means that any n choose k is equivalent to n choose n minus k. Because we built this triangle with sums, it naturally produces Pascal's identity. The last thing I want to touch on is called the hockey stick theorem. The sum of the handle of a hockey stick is equal to the foot. Here's one such hockey stick. Notice how all the white numbers add to the red one. And the foot doesn't need to be at the bottom of the triangle. Even for really long hockey sticks, the property still holds. You're probably surprised this triangle is free given just how much it tells you. For more guidance, take a look at the resources listed below.